Hi. So in our last discussion, we commented that most of the evolutionary forces that we talked about, selection, drift, assortative mating, inbreeding, all of them will end of the day tend to reduce the amount of variation that is present in the population. Whereas the one force that adds to variation in the population, mutation, it seems to be a weak force primarily because the rate of mutations, as we know, is not very high. So there has to be something else, some other way by which organisms or populations will end up getting their variation, and as you might have guessed by now, that evolutionary force happens to be migration. However, before we go into the details of migration, we need to get a few definitional issues sorted out, and the first thing is related to the term itself. Now, when we talk about the term migration in the field of ecology evolution, there are two slightly different ways in which we think about it. So, if you talk to a behavioral ecologist, they are going to simply say that look, migration refers to any movement of organisms or their propagules, means seeds and other juvenile phases in space. Now, this is also the way in which common people in regular day-to-day usage will think about migration. However, if you talk to an evolutionary biologist, they are going to think about migration slightly differently. They will define it as movement of alleles or genes between populations. So, any movement of organisms which is not leading to a change in the genetic composition of the population, that is not migration according to evolutionary biology. So, just to give you one example to make this distinction clear. Most of you are probably aware of this particular fish. This is the famous Chinook salmon. So, as you know that these fishes, they typically tend to breed in streams in US, Canada and other countries. So, they spend most of their lives in this ocean, but just before breeding they come to these streams. They travel hundreds of kilometers upstream, and then they spawn and they die. The juveniles, they hatch, and after hatching they take a massive long journey all the way back to the ocean, grow up over there, but again when the time comes to breed, they come back often to the same stream, well mostly to the same stream, and then lay their eggs. Now, what is this? Is this migration or is it not migration? If you ask an ecologist, they are going to say that look, the individuals have moved thousands of kilometers, so obviously it is migration. But if you ask an evolutionary biologist, they are going to say that look, if we define the population as the fishes of a particular stream, the same fishes, they are going out and then they are coming back. So, in terms of the population, there is no influx of new allele, and therefore evolutionarily speaking we cannot call it as a migration. So, this is the two definitions are absolutely consistent in their own place. The problem happens when one person uses migration in one sense and the other person uses it in a different sense. So, to ameliorate this problem, in many textbooks they use the term gene flow instead of migration. Frankly speaking, it is a better term. However, in many textbooks, particularly the slightly older ones, the term migration is used much more commonly, and that is the one that we are going to use in the context of our discussion as well. Now, in order to figure out what exactly migration does, in what way it affects, it is probably a good idea to take a very toy model in our mind and then see what it does in the toy model, and then extrapolate it into more realistic scenarios. So, the toy model that we have in our case is what is known as the continent island model. So, in this model, you assume that there is a huge piece of land or water, whatever you call it, the continent, and there is a smaller population which you call the island. And let us assume that both are exchanging individuals with each other, but the number of individuals n that is being exchanged, that number of individuals is a constant. Therefore, although there is migration, the population size is not changing either on the continent or on the island. So, then in this context you explicitly assume a one locus two allele scenario, and let us assume that for the allele A1, the frequency on the continent is Pc and the frequency on the island is Pi. The third major thing to be assumed is that the size of the continent, I mean the population size of the continent is much larger than that of the island, and as a result of which, even though there is migration happening to and fro, the allele frequency PC on the continent remains constant, whereas it is only the allele frequency on the island which keeps on changing, and all other conditions of Hardy-Weinberg are valid, which means there is no selection, there is no mutation, there is no drift, etc., etc., etc. So, now the question is that on this we have to think about migration, right. Now, there is a slight bit of a, well, I will not call it trick, it is just a slightly different way of thinking about migration in this particular context, and for this model the way we think about migration is that, let there be a population of constant size in the island, where the migrants make up a fraction m in every generation. Okay, this is the key phrase, migrants make up a fraction m. So, just to give you a numerical example, suppose there are 100 individuals in our island population, focal population, and let us say 25 individuals have come from outside. So, the total number of individuals is 100 plus 25 is 125, and out of this 125, 25 are migrants, which means that m is equal to 25 by 125, which is 1 by 5, which is 0.2, right. So, this is the only thing that you have to keep in mind. Migrants, or rather m, the migration rate, it refers to what is the fraction of the total native plus migrant population, which is the migrants. So, m is equal to number of migrants divided by the total number of the total size of the population. The common mistake that students make when given a situation like this is that they assume that there are 100 individuals in the population, 25 individuals came in, therefore, fraction of migrants is 25 divided by 100, which is 1 by 4, which obviously is wrong. So, if you do not make that mistake, everything else in this context is actually rather simple. So, with this background, we are now going to ask the question, how will migration affect the allele frequency on the island? And in order to do that, we will go to our simulator, here it is, and we will start the tool, we will start the simulations, we will do simple individual simulations. So, remember all other conditions of Hardy-Weinberg are operative, therefore, population size is infinite, and number of generations, let us make it 1000, okay. And starting frequency of allele A1, this is in the context of the island, so this is Pi, so let us keep it at 0.5, it does not matter. And additional settings, click on migration rate, so let us say we will keep migration rate at say whatever 0.25, let us say, and migrant allele frequency, so this is what we called as PC. So, we will keep that, let us say the other one we have kept it as 0.5, let us say we will keep it at 0.9. So, our allele is more frequent on the continent than it is on the island. Excellent. So, now let us run the simulation. We run the simulation and what do we see? So, we see that the frequency of the A1 allele, it starts from 0.5 and then rapidly it climbs and it basically stabilizes at about 0.9, which is the larger of the two frequencies. Okay. So, this is also the frequency that was there in the continent. So, what is happening? Is it settling on the larger of the two frequency or is it settling on the frequency of the continent? How will you figure that out? So, the only way to, or the simplest way to do it is that now we invert the situation. So, we now make the starting frequency of allele A1 as 0.9 and we make the migrant allele frequency as 0.5. If it is settling on the larger one, then it will still go to 0.9, whereas if it is settling on PC, the migrant allele frequency, it should start from 0.9 but go to 0.5, right. So, let us see what happens. We run the simulation and there you go. It starts from 0.9 and very quickly it actually settles down at 0.5. So, it looks like that it does not matter whether the continent's allele frequency is higher or lower, whatever is the continent's allele frequency, it will settle at that value. Okay. You can play with this, with a few more values, and you can actually satisfy yourself that this is what happens. Okay. So, till this point we kept the migration rate at 0.25. Will things change if we change the migration rate? So, let us make the migration rate, let us say we make it 0.35, let us say. Okay. We are just playing over here, any value is fine. So, we make it 0.35 and let us see what happens. So, here it takes about 60 generations to hit 0.5. So, now we do this again and it again settles at 0.5, except that now it is settling slightly quicker, it is taking about 30 generations or so. Okay. So, now let us make it 0.5, let us make it even higher. Okay. What happens? It again settles at 0.5, except that now it seems to be doing it even faster, it is doing it in about 20-21 generations or so. So, basically what happens is that if you increase the migration rate, then the behavior does not really change, it still settles on whatever is the value at the continent, but what happens is that as the migration rate goes up, it goes to that equilibrium value, the continental value, faster and faster. Okay. So, of course, you can play with this on your own and satisfy yourself whether this happens every time or not. So, in the meanwhile, we are going to go back to our slideshow, and here are the two observations that we had. Irrespective of the starting frequency on the island or the continent or the migration rate, the equilibrium frequency on the island is whatever is the frequency on the continent, and the rate at which the continental frequency is reached, the equilibrium frequency, it depends on the migration rate. The higher the migration rate, the faster it reaches there. So, now of course, one has to ask the question, why exactly is this happening? And in order to understand why this is happening, we will do some very quick simple algebra to derive the relationship of allele frequency with migration. And as I said, continent island model, just to refresh your memory. So, we have the continent where the frequency of allele A1 is Pc, we have the island where the frequency of allele A1 is Pi, and one locus 2 allele scenario, and Pc is a constant. The number of migrants exchanged is in both direction is capital N, therefore, population size does not change, and all other Hardy-Weinberg conditions are being applicable. So, there is no selection, there is no drift, there is no mutation, nothing. The only stuff that is happening is migration, right. So, if this be the case, what exactly happens to the frequency of allele A1 on the island after one generation of migration? So, let us assume that we call the frequency of allele A1 on the island Pi after migration, that is what that prime tells you, as now once migration has happened on the island, you have the migrants, you have the natives, right. So, the migrants have some frequency of allele A1, the natives have some frequency of allele A1, right. So, the migrants, we have already said their frequency is going to be Pc, and the frequency amongst the natives is going to be Pi, right. Now, we know that the frequency, the resultant frequency is simply going to be these two frequencies, the sum of these two weighted by their respective fraction in the population. So, what is the fraction of the migrants in the population? By our very definition, that fraction is m. So, this is MPC plus Pi. What is the fraction of the natives? This is m. So, this is 1 minus m. So, now you realize why is it that m was defined in that particular way. The maths become extremely easy in this step. Okay. So, Pi prime is equal to MPC plus Pi 1 minus m equal to MPC plus Pi minus MPI, right, equal to Pi plus, we will take the m outside, Pc minus Pi, right. So, this is the amount by which the allele frequency on the island is going to change. Now, delta p, which is delta p is the amount by which the change is happening. So, delta p is p prime minus pi, right, equal to pi plus m p c minus pi minus pi, right. So, of course, this and this gets cancelled, equal to m into p c minus pi, right. So, this straight away tells us that the magnitude by which delta pi is going to change on the island, that magnitude is dependent on the multiplication of the migration fraction and the difference between the continental frequency and the island frequency, right. So, obviously, the larger is m, the faster the greater is going to be delta pi, and the greater is delta pi, the faster will the island population change. So, that is why if you remember, as we increased the value of m, the whole population, the allele frequency changed faster and faster and went faster to the equilibrium. Now, what exactly happens at equilibrium? At equilibrium, of course, delta pi will be equal to 0, which means that this entire thing, which implies that m into p c minus pi, this has to be equal to 0. Now, this is going to happen in two ways. One way is if your migration rate itself becomes equal to 0, but if your migration rate becomes equal to 0, then essentially you have two populations which each one of them are in Hardy-Weinberg equilibrium, because all other conditions of Hardy-Weinberg are being applicable. So, therefore, obviously at that point there will be no further change, which is a very trivial scenario. But if migration rate is not 0, if migration is continuously happening, then the only way in which your delta pi can be equal to 0 is when p c will become equal to pi, right. P c minus pi equal to 0, which means p c is equal to pi. In other words, at equilibrium, this is the only condition possible. Now, of course, p c can become equal to pi in two ways, either pi goes towards p c or p c goes towards pi, right. But we have started by assuming that p c is a constant. Therefore, the only thing that can happen in this context is pi goes towards p c, which is exactly what we were seeing, irrespective of what the island's frequency was and what the continent's frequency was. After some time, the island's frequency settled on the continent's frequency. Okay. In other words, if you are having continuous migration like this, then after some time both populations, they are going to have the same allelic frequency. This is a way in which it is a homogenizing factor, but the homogenization is not in terms of a loss of an allele or something. It's what is happening is that the two frequencies of the two populations are becoming equal. Now, as we saw, this is obviously a toy case, right, but it is very easy to go from this toy case to a slightly less toy case, and that is the migration model, two patch model, right. So, instead of a continent and an island, now we have a patch 1 and we have a patch 2, or you can even call them population 1 and population 2. So, the only thing we assume over here is that the number of individuals that are being exchanged, that number of individual remains the same in both directions, which essentially means that the m is also the same for both populations. Okay, so, both populations start with the same population size and they are exchanging same number of individuals, and therefore, the population size in the whole thing remains constant. Okay. So, if you have a situation like this, which as you can see is slightly better than, slightly less restrictive than the previous one, then what is going to happen? Then using the same logic that we used for the continent island model, we can say that P1, so this is now for patch 1 dash, is equal to 1 minus m into P1 plus m into P2, right, because fraction m is being made up of the migrants which are individuals from the second population, in which the frequency of the allele is P2. So, m into P2, and fraction 1 minus m is made up of the natives, amongst which the frequency is P1. So, 1 minus m into P1. Okay. By the same token, P2 dash, which is the frequency after migration in P2, is equal to 1 minus m into P2 plus m into P1, right. Now, we need to figure out what is the overall frequency of the allele A1 taking two populations together, in some sense the meta population, right. So, that thing, the overall frequency, now I am just going to call that as P, okay, this total in some sense. P after this thing is simply P1 dash plus P2 dash by 2, right. Why? Population size is exactly the same number of individuals are being exchanged. So, it is simply the average of the two. So, P1 dash plus P2 dash by 2 is equal to 1 minus m P1 plus m P2 plus P2 dash is 1 minus m P2 plus m P1 whole divided by 2, right, equal to P1 minus m P1 plus m P2 plus P2 minus m P2 plus m P1 whole divided by 2. This entire thing is divided by 2. Now, you can already see that I have a minus MP1 here and a plus MP1 here gets cancelled. I have a plus MP2 here and a minus MP2 here which gets cancelled, which is simply equal to P1 plus P2 by 2, which, if this is the previous generations thing, right. So, this is essentially the average allele frequency in the two patches before migration. So, the allele frequency overall after migration is equal to the allele frequency overall before migration. Now, this is not at all surprising. Why? That is because, just think about it intuitively, forget about all the maths. What is happening? We are simply taking n individuals from one population and pushing it here, and another n individuals from this population and pushing it here, right. Nobody is getting killed, there is no sampling, there is no drift, no mutation is happening, no selection, nothing. So, all we are doing is we are just redistributing the individuals from this population to that population, and therefore, very obviously the overall thing, the overall population allele frequency in the overall population, that is going to remain constant, which is precisely what you are going to see over here, P1 plus P2 by 2. Now, what exactly is happening in any one of the two populations? So, as we said, P1 dash is this thing. So, delta P, so let me just so delta P is equal to delta P1, I must say, delta P1 is equal to P1 dash minus P1 equal to 1 minus m into P1. So, I am just taking it from here, okay. 1 minus m into P1 plus MP2 minus P1 dash equal to P1 minus MP1 plus MP2 minus P1, right. Sorry, this dash is not there. So, minus P1. So, this and this gets cancelled, equal to, I will take the m outside, P2 minus P1, right. Now, similarly, this is delta P1, similarly delta P2 will be equal to m into P1 minus P2, okay. Now, again take any one of them, let us take the first one, all right. So, at equilibrium, what is going to happen? At equilibrium, delta P1 is going to be equal to 0, and for that to happen, either we will have to have the situation when there is no migration, which as I said is the trivial case. The other situation in which it can happen is if P1 is equal to P2, right. You get the same condition from here, P1 equal to P2. In other words, if you have two populations which are exchanging migrants, then the entire thing is going to stabilize when the two the allele frequencies on the two patches, two populations become equal, which if you remember is precisely what we saw in the continent island model. So, this is the main thing over here, the main insight, that when you have migration, then the allele frequencies, they tend to become homogenized over space, and this is a very, very powerful way in which it ends up affecting evolution. In fact, this thing migration, it ends up interacting with all the other evolutionary forces that we have seen till now, but those interactions and real life examples for those, that is what we are going to see in our next discussion. See you then, bye.